don't see the set of, I mean, the audience I don't see, but I suppose that I should speak English, isn't it?
Yes, I believe it's better to speak English.
Okay, so I'm sorry then for my terrible English. And second, I'm sorry that I didn't succeed to understand how to write simultaneously on my lunch, on my tablet, and looking at my colleagues who taught me how to do it, said that it is terribly difficult, and I can do it only in double. So I'm sorry for presentation, not for usual presentation. I see Nikita Nikolaev is here. I should ask him because he is great master to do it. So the next time, I suppose Nikita will share with me his knowledge. I will speak today, and the last excuse I would like to ask you my excuses for the subject, because the subject of today's talk, I think is not new at all. It is just kind of pseudo-pedagogical introduction in elliptic Poisson algebras. I'm not even sure that today I will succeed to go to a real world of elliptic algebras. Because Joseph, who is the host of the seminar, asked me to be as much understandable as it possible. I don't know if I will be understandable, but I will try at least to do my best. That's why, sorry for no new results. Almost, maybe at the end I show you something small piece of new result, but very, very quickly. So what I suppose to speak today is mainly based on my old paper with Sasha Adeski from Brock University in Canada. It is strange, but the subject becomes more and more Canadian by Adeski, Gualtieri, Brent Pim, Nikita, who is here, and many other people. I mean, the subject of Poisson's polynomial structures and algebraic geometry behind of it. And that's why it's my pleasure to highly recommend to everybody who is interested in the subject recent lectures of Brent Pim from McGill. He gave during the Poisson 2016 in Geneva, very beautiful 3 or 4 lectures, and then he wrote a survey in letters mathematical physics. So I've used, and I'm very thankful for this possibility. Okay, so plan of my example talk is the following. I mean, to talk about examples is the following. I will very, very briefly remind the definition and some information about Poisson brackets and Poisson structures in general, and then I will fix on example on holomorphic in holomorphic setting, so Poisson structures on complex manifolds. Maybe briefly, very briefly discuss specific of these examples, and then go directly to Poisson polynomial structures, elliptic and non-elliptic. So I'll show a few elliptic examples today, and probably I will tell you the history why elliptic algebras now people are very well I would say very well know these algebras under the name of Sklyanin, Adeski, Feygin elliptic algebras. I will try to briefly to tell you the story how Sklyanin discovered these algebras. And then I will show you some non-elliptic but also polynomial structures which are intimately connected to algebraic geometry, namely structures on K3 surface and on some very interesting class of affine cubic surfaces, which appeared in many different branches of mathematics recently. So let's start. I think that everybody knows, but anyway, I should remind you that under Poisson brackets on a manifold, under manifold M, I will understand or smooth, or algebraic, complex, real, analytic, and at the moment, any manifold M, and I will consider the function algebra on this manifold with respect by pointwise multiplication. And I suppose that this algebra can be supplied with another operation. I will based mainly on the example of complex base field. So it's a C bilinear operation, which to each couple of functions define another function, which satisfy the first skew symmetry property. Then the second, this operation is a derivation of this initial pointwise product, which is just called Leibniz rule, Leibniz rule definition. So if you have a usual multiplication of two functions, then the bracket with the third function gives you derivation in left from left to right. But it is immediately from antisymmetry, you have a derivation by the first argument as well. We are in commutative situation here. And the third, usually it's logically, it would be better to put it on the second place. This operation satisfies to the standard Jacobi identity, which means that the first and the third operation just define Lie algebra structure, infinite dimensional Lie algebra structure over C, and additional data, it's a compatibility condition of these two operations, bracket and pointwise multiplication. Now I want to be a little bit more, a little bit more, no. Okay, I think that something happened with my, yes. Something happened with my next slide. Anyway, I wanted to say that instead of Poisson brackets, we can speak about so-called Poisson structure. And this under Poisson structure, people usually understand the following. I will try to save the situation. So let's suppose that we have a manifold which from my category, and then Poisson structure. This Poisson structure is a two-tensor field P, which is Q-symmetric, and defines the bracket operation for two functions f and g by coupling with the two-form df dg. And then all these conditions which we for this bracket, they are impose on pi the following. So this is a skew symmetric. It is by definition clear from this definition, skew symmetric. So it is a section of lambda 2 of Tm. And also there is operation in the exterior algebra of vector fields, which are sections of tangent bundle. And this operation, which is usually called a Schouten-Ninius bracket, gives a condition of Jacobi identity for this bracket, which is equivalent to nullity of this three tensor field. So this operation to two tensor field pi assigns three tensor field pi comma pi Schouten brackets, and this is should be zero. Then it guarantees you Jacobi identity for the bracket. So it's a master equation or pilot equation for Poisson structure. So this is a bracket. This is a slide which disappeared. I don't know why. And then the last general remarks about Poisson structures per se. I should just remind you that there is an important notion of so-called Casimir function of Poisson structure, and the function called Casimir if it Poisson commutes with all other functions from the algebra on M. And I want also to say that one can think about Poisson structure like a kind of generalization in some sense of symplectic structures. So if this tensor pi is non-degenerate, then one can consider the inversion of this, and we obtain the very famous notion of symplectic structure, which I'm almost will not consider, so I don't want to discuss it in details. But in general, this structure might be degenerate, and also it is interesting to study two sets of points associated with this tensor pi. Zero Lotzi and degeneration Lotzi. So with this, at this moment, it is very nice to consider the set of points where this tensor anyway non-degenerate. This set of points usually people call symplectic leaves, because if you restrict your tensor on this set, you obtain invertible tensor or symplectic form. But the behavior of this set of symplectic leaves, it depends on very, very strongly on the rank of Poisson tensor. So in the neighborhood of so-called regular point, we have a good symplectic foliation, and this symplectic foliation one can imagine like a unification of varieties given by set of constants. So on each such intersection, our tensor field, bivector tensor field pi is not degenerate, but in general, this regularity might be very, very rare. And it means that there are irregular points as well. And we will be interested in this case also. Such situation very often happens if we consider holomorphic or complex Poisson structures. So this is this means that in local coordinates on a complex Poisson manifold. So in my talk, I will suppose mainly complex Poisson manifold which are projective It means that one can consider this manifold which admit embedding in a projective space of some dimension. And also we will consider affine counterparts of these structures. And this is main class of manifold in my talk. Here, this bivector field is a section of holomorphic second exterior power of holomorphic tangent bundle, or if you want to think in terms of sheaves, you can consider this like a section of holomorphic second exterior power of sheaf of holomorphic vector fields on M. Okay, the condition as well you can consider in this holomorphic in third exterior power of your holomorphic vector field, and also the functions locally which define the by pi, they define these brackets between holomorphic function in the usual way, like I reminded you before. What is interesting here? It's consider even in simplest example, if you have, for example, C2, this example belongs to Richard Goto, and it was used by Brent in his lecture, so I just copied this illustration. For natural dimensional reasons, this bracket is just a function of holomorphic function of two coordinates, z and w, z and w. So no constraints from Jacobi identity, because no third for C2, no third exterior power. So any F defines this structure. But if you want to study a presentation of this bracket in local coordinates, it will be different from the behavior of this function. So, for example, if you consider away from zeros of function, you can easily invert your tensor. It means you just need to consider two forms, dz dw wedge dw divided by f, and by changing of coordinates, you can obtain by Darboux theorem, by holomorphic Darboux theorem, you can obtain dp dq. So in this violet area, you can always find Darboux coordinates for my bracket. But if f equal to 0, the situation might be quite different and change drastically. For example, if you have just a simple zero, in neighborhood of simple zero, the normal form of your bracket is just, you can find the coordinates instead of zw. It denotes on the picture of Brent by y and z, and then the tensor is y dy dz. It means that your function can be always taken like z here in my notations. But if you have a multiplicity, then in the neighborhood of multiplicity, situation is becomes again much more complicated. So there are different normal forms, local normal forms. It depends on the behavior of f. It is interesting that f, if you consider polynomial structures, it means if you sorry.
I'm
if you
sorry,
can see.
Volodya. I'm sorry, just one question.
Yeah.
F is function of
Yes,
z
sure.
and omega. It is function, analytic, holomorphic function of z and omega in your example.
Yeah.
F is it right that F is a function, holomorphic function of z and omega in your example?
Here.
Yes, yes.
Yeah, of course, it is locally, it is a holomorphic symplectic structure.
Yes, but it's function of z and omega. Okay, thank you, thank you. Just
here this you can always make Darboux coordinates. It means that this form omega in the violet area, it is constant.
Okay.
It's a symplectic constant, dpdq, if you want.
Yes, yes. No, it is
dpdq. You understand? So it is special choice of coordinate, which is most simple.
Yes, yes. Thank you, thank you.
Again, another example of complex Poisson manifold, it's a well-known example of coadjoint orbits of complex Lie algebra, and the corresponding symplectic leaves, they are coadjoint orbits of Lie group corresponding to this algebra. I will be a little bit more precise with this example just in few minutes, because I want to show that this example is just an example of so-called Jacobian Poisson structure. Much more interesting the example when you take M equal P2 as a projective space. And the projective space, of course, it is also a Poisson variety, which has symplectic leaves of two types. First, it is symplectic leaf of dimension 0, which are points on cubic curve. And you will see very easily, one can see how it works. And if you take this curve away, here the example of degenerated cubic curve with double point. And so you see a part of this curve, you have two-dimensional symplectic leaf, and also you have red zero-dimensional. Each point on this curve gives you zero-dimensional symplectic leaves. Now we want to discuss this example a little bit more precisely. For this, I start with a reminder what's happened in general if you take two-dimensional Poisson complex manifold. In this case, you can identify the exterior power, second exterior power of holomorphic vector fields lambda t with the so-called anti-canonical bundle Km-1. Anti-canonical bundle, it's in some sense dual to canonical bundle. In canonical bundle, it's a determinant bundle of cotangent, holomorphic cotangent space T star M. And this anti-canonical bundle defines so-called anti-canonical divisor, zero locus of section of this line bundle. And this structure for any M vanishes on cubic, possibly degenerate curve, like we want to argue. For example, if you take the case of P2, then anti-canonical bundle K-1 P2, it is just a line bundle of degree 3 polynomials, and the Poisson tensor pi, in this case, vanishes on a cubic curve given by cubic equation f x1, x2, x3 in homogeneous coordinate in P2. And it is very, very easy to check if you take just three standard charts of P2 with x1 non-zero, x2 non-zero, and x3 non-zero, and you take overlap of two of this. So if you take u1, where x1 non-zero, and u2, where x2 non-zero, then you can introduce here two coordinates u and v. U say x2 over x1, and v x3 over x1. And here u tilde, which is x1 over x2 and x3 over x2. And then you can take in the relations between u and u tilde, v and v tilde, v and v tilde. You can immediately obtain that the function f, which in coordinates uv or u tilde, v tilde, always have these brackets, you know, f of uv, and this function f should be a polynomial of degree at most 3. This is important fact, proves that it is just simple computation, show you why the divisor, anti-canonical divisor for always has degree not bigger than 3. Now, it is interesting to see how different might be this zero lossy, and you will see these various cubic curves in P2 like zero lossy, possible zero lossy. And I took this nice picture from Brent Pim, but of course this picture is super known, especially for people who are doing algebraic geometry. I will just in 1 minute show you another picture. So this is a smooth elliptic curve, which also can be zero. And if you take P2 minus this elliptic curve, you obtain non-compact symplectic holomorphic manifold, which is a kind of non-compact Calabi-Yau manifold, which is important. And then you can consider nodal cubic. We have seen it. Cuspidal cubic, and then conic and line in different configurations, intersection line and conic, tangent line to conic. Very important and nice example of three lines, because this is the divisor of singularities for affine cubics, which appeared recently in a study of monodromy data for Pendevé equation. I will show you probably or today or next time. And also G. This is a possible, also possible degeneration of cubic curve in P2. And in each case, you can find some very strange, sometimes very strange Poisson structure, very degenerate Poisson structure. Why it is amusing? Because if you know a little bit the theory of elliptic fibrations over projective curves, then you immediately recognize in these pictures so-called singular fibers, except smooth fiber. There are always so-called Cadeira neuron models for singular fibers of elliptic surface fibration. And these 6 examples, they are in one-to-one correspondence with 6 examples, 1, 2, 3, 4, 5, 6, in this picture of Brent Pim. And this, it is interesting. Recently, we have used this description of elliptic fibrations when we study generalization of this configuration of three lines for so-called Calabi-Yau Pendevé Sklyanin type. we will probably Thursday, Marta Mazzocco will speak about it in Global Poisson seminar. So I invite you to think about what I told you today when you will hear her. Okay, what's happened in Poisson threefolds? In the Poisson threefolds, you have, of course, the same condition, but this is the first time, I would say it is a minimal dimension when this Schouten-Ninius integrability condition is non-trivial, because for surfaces it was trivially for dimensional reasons, but here it is not. And here it is interesting that studying this lambda 2 of Tm, you can identify it with one forms with values in anti-canonical bundle. So to each tensor pi, which is a section of lambda 2 of M, you can assign one form theta with values in k minus 1 m. And the condition p times p for Jacobi identity of your structure, you should just solve the equation theta wedge d theta of this one form, vector valued one form theta. This is a very easy computation. I invite you to do it yourself. But this very easy computation, for me, I spent 15 minutes just to check it carefully, but it is. And then this, you have more complicated Poisson symplectic foliation, which relates to these Poisson structures on threefold. Of course, they are much more interesting. There are foliations which are, there are leaves which are not zero lossy of the Poisson tensor, but zero lossy of this one form theta. And this Poisson and this symplectic leaves, they inherit Poisson structure on the intersection on the zero lossy of P. And typical example of this intersection and Poisson bracket on this is just Sklyanin initial algebra. You will see it. Let's consider now some examples of threefold Poisson structure. The first example, it is just a so-called Jacobian structure in affine space C3. Let's consider any holomorphic non-constant function, and then amazingly this defines for free Poisson tensor P sub phi sub f, which is defined by the volume form on C3, or if you want three tensor exterior tensor GDEx1, GDEx2, GDEx3, and the contraction with differential of f. This immediately gives you that taking corresponding one form df as a theta, then the condition theta wedge theta d theta trivially satisfied because of d square equal to 0. So you have for nothing Poisson structure for any holomorphic function f. And
sorry,
structure,
Volodya.
Yeah.
Volodya, I'm sorry. The second line, this pi f, you have a three vector, yes? Dx, dx1, dx, and then df is yes, it is one form. Yes, okay, yes, okay, thank you.
If you have questions, please ask freely. Stop me and ask. In coordinates, it is very easy to check that the brackets between any function big F, big G define this defining by this pi F, pi sub F. This bracket defines through Jacobian of three functions big F, big J, and small f with respect to the coordinates x1, x2, x3. That's why such brackets people call Jacobian Poisson brackets, and corresponding structure is Jacobian Poisson structure. And this is just a very, very simple structure, but appears in many, many useful situations, even in geometry of K3 surfaces, as you will see. The very function f, of course, commutes with any function on C3. So we have a Casimir of this Jacobian structure given by this f, okay?
Can you say?
And symplectic leaves, yes?
What is the Jacobian? What is the meaning?
Sorry?
What is the, you mean like the...
Jacobian, it means that you have a determinant of Jacobi determinant with respect to these coordinates. So first line f, the derivation f by x1, by x2, by x3. Second line, derivation of big G by x1, by x2, by x3. And third line, derivation f by x1, x2, x3. So you have 3 times 3 determinant, and this 3 times 3 determinant define you a function. And this function which you assign to these two functions f and g. Of course, it depends on f. So this is why this structure is called Jacobian Poisson structure, because this bracket is nothing but Jacobian of these three functions with respect to dx, dx, d2, dx1, dx2, dx3. And it is very easy to look the symplectic leaf structure. So you have two types of symplectic leaf. First of all, zero-dimensional. They are critical points of f, where differential equals to 0. And two-dimensional, they are defined by preimages of just surfaces which preimages of C non-zero C in C3. So now the example of this, I promised you that the example of linear Kirillov constant, Lie Kirillov constant, Berezin, Suryo bracket on G star can be interpreted in terms of the linear Jacobian structure. Linear because the dependence, coordinate dependence is linear here. So let's choose the coordinates on G star of SL2C by x1, x2, x3, and then the Lie algebra relations for SL2C define the corresponding Poisson brackets on G star, x1, x2 equal to 2 times x2, x2, x3 equals to x1, and x3, x1 equals to times x3. And it is immediately follows that this it immediately follows that this brackets, they are Jacobian with respect to the function f, which is a Casimir of this bracket, 1/2 x1 to 2 times x2, x3. If you check, it is immediately. And the brackets, of course, define in the usual way with this tensor PF. So this is an example of linear Jacobian structures. And the corresponding foliation is very well known as well. The symplectic leaves of this bracket, they are orbits, and these orbits for SL2, here of course it is real version of it. You have non-singular hyperboloids, and you have a red cone. They are two-dimensional, and zero-dimensional singular point in the origin where your differential of your Casimir equal to 0. So this is a critical point. So this symplectic foliation of 0 and two-dimensional leaves. And finally, this is an example also, another example of Jacobian type, which will be studied very carefully in the next part of my talk. This is a so-called Artin-Tate-Sklyanin elliptic Poisson algebra. So now we come back to P2, and we have a normal smooth elliptic curve. This cubic, which embeds in CP3 with the help of linear systems of line bundle of degree 3. And this line bundle of degree 3, the section of this line bundle, they are nothing but 3 theta function of level 3, theta 0, theta 1, theta 2. And the relation of Hesse gives you the equation of this normal elliptic curve, which is written here. So you have cubic part, and you have a module K, which is defined by module of your elliptic curve. And the bracket between x1 and x2 defined by derivative by x3 of this cubic expression. So it is again Jacobian. You can ask how it comes. You spoke about Jacobian in C3, it means in affine space, and now it is they are homogeneous coordinates in P2. In a few minutes, I will explain the relation between Poisson structures on affine part of projective space and vice versa. But I will postpone this Artin-Tate-Sklyanin, and why it is Artin-Tate I will explain also later, in my next talk, because this is just a the most simple example of so-called Odesky-Feygin-Sklyanin Poisson elliptic algebras. Okay, now I want to go to the most interesting example because it was the origin of all the story. Let's consider like a threefold P3. And the anti-canonical bundle will be a line bundle given by polynomials of degree 4. Then, if you want to write the corresponding one form theta, let's choose 2 sections of degree 2, so two quadratic polynomials on P3, and define this theta like S1 ds2 minus S2 ds1. Then condition that theta times d theta equal to 0 gives you a Poisson structure. And this Poisson structure defines in this geometric language as follows. You have a Poisson structure which defined on the 0 of this form, and this is a 2 quadric surfaces, Q1 and Q2. The intersection of these two quadrics gives you also a Poisson submanifold, and this Poisson submanifold is a cubic curve. And in our main example, it will be a smooth cubic curve. And this was just an elementary picture how to look the intersection of 2 quadrics in P3. And you know, since Jacobi, that the intersection of 2 quadrics in P3 can be uniformized by 4 Jacobian theta functions. So these 4 Jacobian theta functions will Sklyanin very intelligently translate in most simple elliptic function, you will see, and then it gives him the first definition of quadratic Poisson elliptic structure. So I want to make a small digression, because now I don't want to cover that it is possible to generalize immediately my Jacobian Poisson structures, and instead of 2 polynomials which define you 2 Casimirs in 3-dimensional space, consider any dimensional space Cn and n-2 polynomials q1 etc. qn, and then for any lambda polynomial or constant, it doesn't matter. You can define bracket between 2 functions on Cn, or between 2 polynomials if you want, by the following generalization of Jacobian. You consider so-called Nambu Jacobian. This also Jacobian, of course, with n-2 Casimirs and 2 arbitrary function f and g. You divide it by the volume, and you obtain some new function. The property of this bilinear differential operators of Nambu type gives you that this is a Poisson bracket in very, very general setting. So this is exactly, again, the case of Sklyanin. You have 2 quadrics. Let's consider one quadric like x1, x2, x3 in homogeneous coordinates in P3, and add the first coordinates and take some constants j1, j2, j3 in front of squares of the first 3 coordinates. Then you have 2 quadrics in affine space C4, or you can consider the corresponding projective analog of it, which I just remind you. And the brackets between x1 and xj, they are very easily computed from Jacobian property, like determinant of partial Jacobians. So here, if you take I and j coordinates, then to find the bracket between these 2, it is just take this q1, q2, and derive it by complementary coordinates L and K, which are not I and J. And then it depends on the sign, of course. And then you obtain bracket in a fine part of P3, and also in P3, as you will see. And this bracket, it was a bracket which Sklyanin defined. I will tell you the story of this discovery. The story goes back to so-called golden age of inverse scattering method, which was developed in St. Petersburg at that time, Leningrad School by Fadeev, Sklyanin, Kulish, and other people. And in its classical version, the inverse scattering method reduces to the following 2 problems. First problem, you should find the solution of so-called classical Young-Baxter equation, which depends on parameter. And this is a Young-Baxter classical equation, and this is R matrix R. The sub indices, I'm sorry, I have no time to explain it again for those who never met it, but I remember that in Joseph's seminar, I told in details about this classical Young-Baxter equation in all its forms. So this is the so-called Leningrad notation, and you can easily recognize that this relation in lambda 3, because R should be antisymmetric or just antisymmetric plus some invariant tensor. So Sklyanin found the solution of this Young-Baxter. And this solution he found in study of special model. Of course, it is not for nothing. He studied so-called Landau-Lifshitz model. And for Landau-Lifshitz, Sklyanin discovered that this equation is solved by the following 4 times 4 matrices. he considered three Pauli matrices, sigma sub alpha. Everybody knows what is a Pauli sub three Pauli matrix, so I will not remind you. Then and coefficients of tensor product of Pauli matrices are given by Jacobi knoidal functions. The first coefficient, it is 1 over sn. Second, it is dn over sn. And third coefficient is kn over sn. So all these functions are appeared from elliptic integrals, and they were introduced by Jacobi in the first half of 19th century. So it's a classical analytical thing. And then second part of the scattering method is find the solution lambda of u, L of u, of the classical analog of so-called RLL or RTT equation. The quasi-classical analog is a Poisson relation, Poisson bracket between this matrix operator L1. It means that you take in tensor product L on the first tensor space and 1 in the second. And L2, you have 1 in the first tensor, in the first half of the tensor product, and L in the second space of the tensor product. So this, and here it is just a bracket of 4 times 4, if you want, matrices. R, it's solution of your Young-Baxter. And L1, L2, it's just a product of this L operator. So if you know R, you can try to solve this equation for L. And Sklyanin succeeded to do it. First of all, by definition of these coefficients W sub alpha, you can easily check that they satisfy 3 quadratic relations, alpha, beta, and gamma. But only 2 of these quadrics are independent. And this gives you idea. You have 2 quadrics and 3 coordinates, if you want. So you can try to find some. It is just a special case of embedding of elliptic curve in P3. And of course, it is the case. So you have this quadric. And Sklyanin said, let's make the following ansatz to find the solution. L of u we will find in the form x0 plus I, w alpha, x alpha, and your Pauli matrix. So here x0 and x1, x2, x3 just variables. You don't know. And you put it in RLL. And when you put it in RLL, what you obtain? You obtain, first of all, that classical Young-Baxter just immediately automatically satisfied. And then you write another condition, and this another condition satisfy if between x0, x1, x2, x3, there are quadratic relations of this Poisson type. Because you remember that is RLL, it is a Poisson relation. So if you put L in this relation, you obtain these relations between variables x1, x2, x3, x0. And this was the main Sklyanin discovery. If you look and put the corresponding G in your Sklyanin quadric, you obtain the same algebra. So Sklyanin was very, very modest. He said, my aim just to try to attract attention of mathematicians to study this beautiful object. Probably this object should have very serious and important meaning. And then it is indeed the fact. Sklyanin algebras and their quantum analogies, they will be subject of my next lecture. Okay, now I want to say a few words, as I promised you, about how Poisson structures in affine and projective space are correlated. It was a folkloric theorem, which probably in the first time I knew this theorem from preprint of Alyosha Bondel and from the independently from Sasha Polishchuk paper of '99. And this theorem is the following: if you have a quadratic homogeneous Poisson structure on the affine space Cn, Z sub I, Z sub j equal to product, sum of products zk zl with a 4 tensor R I j k l, then this homogeneous Poisson structure define a holomorphic structure on Pn minus 1 with corresponding homogeneous coordinates, just immediately. And then it is interesting that it is true, conversely, is that any holomorphic structure on Pn minus 1 can be obtained from some quadratic homogeneous Poisson structure on Cn. What is less evident but very simple also, that there is a constraint which imposes the conditions that you can extend affine Poisson structure on Cn to holomorphic Poisson, given affine Poisson structure on Cn to holomorphic Poisson structure on the corresponding Pn, if big X are just affine coordinates which correspond to coordinates, homogeneous coordinates in Pn. And if you can extend it, then maximal degree of the structure, it means the maximal length of monomials, is 3. And if you write this condition, you immediately obtain that it should satisfy to this. And this technical proposition, in fact, very important, because if you look the next example, and the next example,
Volodь, just a moment. The previous slide, please.
Please.
What, I do not understand the notation. Yeah, this one. Oops. What does subscript 3 mean?
It is written here.
At brackets.
It means that you have this bracket has a form xi times monomial of degree 2, which I denote by y, and minus xj times monomial degree 2 yi. That's what it means, that this bracket has no more degree than 3.
Strange. Okay, thank you.
Okay, it is very technical. I mean, technical, very easy, but very technical condition. I will explain why it is interesting. Because if you consider the next example, and the next example is so-called K3 surface. I remind you that K3 surface is two-dimensional compact complex manifold such that there exists a non-zero everywhere holomorphic 2 form on this manifold, and the first Betti number of this manifold equal to 0. This is a very interesting and very famous class of complex surfaces, which are all isomorphic, like smooth varieties, but they are very different from the viewpoint of different complex structures on them. And of course, there are different projective models. The most famous 3 or 4 models, I will not touch ramified sextic, I will just try to discuss the most famous. Zero locus of quartic equation in P3, so it's so-called Fermat quartic, x0 to 4 plus x1 to 4 plus x2 to 4 plus x3 to 4 equal to 0 in P3. And two complete intersections, transversal intersection of quadric and cubic hypersurfaces in P4, and transversal intersection of three quadrics, Q1, Q2, Q3 in P5. In all these three cases, you can define Jacobian Poisson structure. I will just show you this in the case of Fermat quartic. If you have this, but all definitions are this, roughly speaking, for those who want some abstraction without coordinates, you can just consider as a corresponding holomorphic symplectic non-zero everywhere form, which is people called Mukai form on K3. You can consider just a so-called Poincaré residue along these zeros of the corresponding projective embeddings of hypersurfaces of quadrics, cubics, and quadrics, and quartic and P3. And this, you take this residue of Poincaré residue in each cases. It works like this. If you have homogeneous coordinates in P3, then you can make a chart where, say, x0 and non-zero, then this equation can be written in terms of function f of x1, x2, x3. And for any two locally defined holomorphic functions, you can define the bracket between this g and h in the form of Jacobian, like you see before, dj, dh, df over dx1, dx2, dx3. This is what in coordinates is given by the Poincaré residue along these zeros in P4. So you take the basic form in P4, which is it is easy to write, and everybody knows how to write the basic form. It is a 3 form, and when you take the residue, you obtain the 2 form, and this 2 form defines the brackets like this. So you can write in different charts, you can write different symplectic non-zero form. Okay, and then you ask, is it possible to extend this Jacobian form on the K3 surface to the whole projective space to be again holomorphic? And it's happened that no, because you remember that before all brackets, they were quadratic in all my previous examples, in Skrianian case, etc. If you write this all three K3 models, you obtain brackets cubic, and then when you extend it, you obtain that you need more degree, so you obtain polynomial degree more than 3, which is contradict to our proposition with Odesky. So this proposition shows that you can't extend this 3 in all 3 models. You can't extend the corresponding brackets to the whole P3. You can say, okay, this is not very deep, because it means only that you can't extend it in this concrete form. But in fact, you can prove, you can make a little bit more effort and prove that it is impossible in any form. So this constraint which we introduced is very important. So this is a good point to stop, and my time, I'm a little bit overdue. So I'm sorry, and thank you for your attention. Please, questions if you want.
Thank you. Let's thank the speaker.
У меня вопрос по этому слайду. Вот здесь внизу отношение двух дифференциальных форм. Это такого типа производная, вот, GH скобочка. Это имеется в виду...
You mean this one?
Yes.
No, it's a function. because you have three form, and you divide it by volume, you obtain a function.
Это обычный EKPA.
Below volume.
This is just Jacobian. This I told you, it's a Jacobian of G, H, and F.
I see. Thank you.
And if you, this is of course a usual Jacobian, but if you take, for example, cubic and quadric in P4, then you need to take partial Jacobian like it was in Sklenin type. But the difference with Sklenin, that Sklenin was quadratic, and this will be cubic. All these examples, they are cubic. For example, for in P5, you have three quadrics, and you have a corresponding Jacobian as well. And when you compute this Jacobian, it 3 times 3 Jacobian will be 3 times 3 Jacobian. The degree of bracket also will be 3. I didn't have time to say about this Dubrovin-Ugalia and Sklenin, but I will speak. Probably I will show you this example next time if you want. I mean, next.
Thank you very much.
Also, I should say that here I have just projective models, usual projective models of case 3. But for those who are interested in it, is as well, if you have a generalization and it exists, the generalization of Poincaré residue for weighted projective space, you can define the same Poisson structures on the models of case 3 as an intersection in weighted project, which is in mirror symmetry. It is very, very important. So you have as well a definition of Poisson structures on this.
Okay, so we will have a continuation next Monday. Yeah, thank you very much.
You are very welcome. Sorry for my bad English.
Well, what can we do?
Will the notes be posted anywhere?
Ciao.
Do the notes for the talk get posted anywhere?
Notes, of course, if you want, I can post.
Yeah, that would be great.
I can put it just in the chat if you want.
Okay, that's good.
So, any more questions?
Can I ask actually if this this symplectic form on the K3H doesn't extend to all of P3, but
no, it is not.
It does not extend, but can you extend it as some other type of structure or like?
No, that's what I told you. Not only this structure, but any Poisson structure on K3 can't be extended to P3, P4, P5 because it is a contradict to our abstraction, degree abstraction. I don't understand what's happened. I have my file, I put,
So, more questions? And thank you very much.
If you want to read the details, why it is impossible for, you can read our paper with Sasha Odesky, which I quoted. And in this paper, we argue why it is not possible even for any structure. And I want to warn you that this file, I think it contains one more slide, which I had no time to discuss. I will start with this slide because it's important and interesting.
Well, any more questions, comments? If there are no, let us thank the speaker again.
Bye.
So